In this segment, we'll finish up the discussion of inventory lot, and we'll look at that other object-oriented way to specify comparison of objects. Now, a tree map works fine with trees that implement comparable, but the map uses, right here in inventory lot, has order as the key type. And order doesn't implement comparable. Here it is right there. No implements comparable in order. So, how do we know, or how will the map know, how to compare two orders? Now, we could, of course, have order implement comparable, but there are cases where you need to compare objects of a class that you cannot modify. For instance, a third-party library class. You can't just add implements comparable in such a class. So, let's imagine order cannot be changed to implement comparable. Instead, we can pass a rule for comparison directly to the tree map as a constructor parameter. And the tree map object will then use this rule to compare two orders without calling any compare to method on the orders themselves. And it does not, by the way, require that the objects implement comparable at all. A typical comparator class implementing comparator just overrides compare with no other members or methods. And inner class by name comparator back here in the inventory lot is a good example of this. It's a comparator class that compares two orders based on the name of the component that they're ordering as returned by getCMPName. You can see that it implements comparator order and then overrides compare, and the override takes the two order objects, gets their component names, and calls strings compare to, that is strings compare to method going there, on the two component names to get a result. Now, the final step is to create one object of class by name comparator and pass that object to the tree map constructor, as we do here on the last line of the inventory lot constructor. The tree map will then call that object's compare method to compare order objects. And here's the first question for you. Just to be sure you've got the idea, write two lines of code. The first one creates a by name comparator, and the second one uses it to compare two orders. Call them O1 and O2 to see if the first is less than the second. So I'm going to put that declaration up and then ask you to fill in those two lines. And returning from a bit of a pause there, the first thing you're going to need to do is do a declaration and creation of a by name comparator. And we could do that thus. By name comparator, CMP we'll call it, equals new by name comparator. And then if we want to do the test I asked for, we would just ask if CMP dot compare O1, O2, what do we ask for? Less than? Then we just need to ask if that's less than 0. Okay, question 2 then. What if we want the order keys to be sorted in reverse order in the tree map, back in inventory lot here? Make a small change to inventory lot that will accomplish that. And this can be done with a single character. I don't know if that was a brain teaser or not, but the single character I had in mind anyway was just put a minus sign on the return from the compare. If you negate the return result by adding that single minus, then what was a less relationship becomes a greater, and vice versa. And you know, as we said earlier, you can use any rule you want for the result of compare to or compare. And this includes effectively lying about the order and producing exactly the opposite result, swapping less for greater. Any classes using this comparison result will be none the wiser, and they'll be tricked into sorting in descending instead of ascending order. Now, the two-step process of declaring a comparator class, like by name comparator, and then using it to allocate an object for it, that was perhaps just a little too tedious for the Java designers, so they added a feature called an anonymous inner class. And this combines those two steps into one for use in cases where you want to create a small class and then make only one object of it. Now, this feature is a bit controversial, as you can tell from my tone, and it's very Java specific, so we'll touch only lightly on it. You don't have to use anonymous inner classes, but you should know how to read them. So, the commented code here in the inventory lot constructor shows how this feature works. Now, the syntax is a sort of mashup of a class declaration and a new expression. And the large expression both defines an inner class, and this is one big large expression here, implementing comparator order, including an overridden compare function, and it also allocates a single object of that class. The defined inner class has no name, thus the anonymous. And this monster expression thus produces a reference to a comparator object, and if we pass it to the tree map constructor, as we are doing here, that whole expression there is being passed to the tree map constructor, then it will use the allocated comparator object. And to break it down exactly, the anonymous inner class syntax is, first, a new expression that appears to allocate an object of a base type, like new comparator order. It may use either an interface or an actual base class. And the parentheses are required, as they would be in any new expression. If the base class has constructor parameters, you can pass those in those parentheses right here. Now, after the new expression is the same brace enclosed code that you would supply for a normal subclass. Note that the braced code in this example anonymous inner class is identical to the braced code for by name comparator. Now, this defines the subclass that will actually be allocated. And that's it. The allocated object is not of the base class or interface, but rather of an anonymous subclass defined by the brace enclosed code there. Okay, now that we have uses set up as a sorted map with order keys and integer values, we can use it to track how many parts as the integer value a given order used from this inventory lot. Each time an order uses a part, it calls usePart. And that method increases the part count associated with that order in uses and reduces the overall count of unused parts in the inventory lot. So read this method carefully and answer this question. What exactly is the val equal null, choose one else, val plus one? What's that expression doing in the put call? And when would val be null? And after a bit of thought there, well, if there is no entry yet in uses for the key ord, for that order, then val will be null, since get returns null for the value of a missing key. And we should insert a 1 for the first use of a part by that order. Otherwise, we should increase the non-null val by 1 and insert that, replacing the old value. In question 4, just one more to reinforce some map concepts. Rewrite usePart without the variable val. Get rid of that altogether. By using contains key instead of checking for null. And that'll reduce these last two lines to just one line. Turning from a pause there. I had this, uses.put on ord, and then uses.contains key as the question mark test, and uses.get ord plus 1 if it does contain the key for that order, and just an initial 1 if it doesn't contain that key. Now, in the next segment, we'll step back a level and look at the inventory class, which has a sorted map of inventory lots in it.